That business about the fusion rules, I haven't looked at carefully yet. The confusion about the numbers, I'm sorry. When I get that clear, I'll come back to you. But let's go on with our, not the fusion rules, the null states. The null states. Let's go on to let's continue with our explicit construction of this R, 1 null state. So you remember we were looking at the minimal model with P and P prime. We have, was it P prime by P or P by P prime was T? We had P, just a minute, unitary. Sorry, where was this? Does somebody remember? T was, this T that we often use, was it P by P prime or P prime by P? Let's see, so H was given in terms of this thing in this form, and I think we'll change it if we, I think T was equal to P prime by P, and we have the usual formulas for C in terms of the central charge in terms of C. In terms of this T, if we need it. Okay, and you remember that we had we were looking at this operator phi R, 1, and then we done the strange construction. The construction went as follows. We first defined these matrices J0, which was the usual 2R plus 1 dimensional R plus 1 dimensional matrix for SU2. Okay, so J0 was equal to R by 2 minus 1 to minus R by 2. This was this matrix. Okay. Then we also defined these slightly unusually normalized J plus and J minus. Right, we had this operator which was J minus, which we defined as delta I J minus Ij to be delta Ij for I is equal to Ij plus 1 for I is equal to 1 up to R minus 1 and is equal to 0 for 0 otherwise. And then we had J plus Ij, which was defined to be a delta I plus 1j, but then with some numbers. And the numbers was I into R minus I. Okay? And this thing was 0 otherwise. So this thing was 0 if I was equal to R, and this thing was 0 if J was equal to, this was 0 if J was equal to R. Anyway, you know what I mean, right? It was this lowering matrix and this raising matrix. Okay. So we had these matrices defined here, and then we defined this operator D. This operator D, which was equal to J minus, maybe minus J minus, plus sum over M is equal to 0 to infinity, minus T times J plus the whole to the power M, and then L of minus M minus 1. Okay, this sum was defined from 0 to infinity, but since j plus to the power r was 0, the sum effectively went from 0 to r minus 1. Okay, now the point of this operator was this. We looked at the equation d times f1 to fr is equal to f0. This operator, by the way, is an operator on a tensor product space. The tensor product space is the Hilbert space consisting of representation space and this R columns. Okay, so each of these F's are vectors in representation space. Okay, so we looked at this equation d of f1 on fr was equal to f0 blah blah blah. Sorry, not blah blah blah, 0. 0, 0, 0, 0. Okay, so now this was our equations for r minus 1 variables. The r minus 1 variables being f0, f1 up to fr. We could use these r equations to solve for any of them in terms of any others. Sorry, we could use the r equations to solve for r plus 1 r equations to solve for r of them in terms of any one of the others. Okay, and our strategy was that we would express fr as some object, we called it delta, I think, on f0, and the claim was that this delta acting on the lowest weight state gave us the singular vector. Okay, all this you remember. And I wanted to prove this claim. That's what we're going to start today's class with. So the first thing that's useful to do is to write down sort of explicitly what we get. First, let's work this this object out a little bit row by row. So we did this last class, but just to remind you, suppose we look at the last row of this equation. Okay, this guy was a lowering operator. Okay, so one of the entries on the last row was minus fr minus 1. Okay, this guy was a raising operator. Okay, so if any number of these j's act, this raises it and gives you 0. So the only one that contributed here was the guy m equals 0. In the case m equals 0, we got this to the power 0, and this was just L minus 1. So plus L minus 1 of fr was equal to 0. Okay, so that allowed us to express fr in terms of fr minus 1 or fr minus 1 in terms of fr. Okay, let's look at the next equation, the next row. The next row was if we act with the lowering guy here, it's fr minus 2, right? So minus fr minus 2. Okay, and now we get two terms. First we get the term that we get by acting with m equals 0. Okay, that will give us plus L minus 1 fr minus 1. Clear? On the r minus row? But in all the terms we've looked at so far, we're looking at j plus to the power 0. Right? But now we're going to come to the coefficients, because now we will look at this guy to the m equals 1. Okay, that raises the guy from fr. Okay, so we will get plus, now coefficient, we'll work out the coefficient in a minute. There's a minus t times plus some number times fr and L minus 2. Right, now what is the number? The number we read off from here. So we wanted to be in the r plus 1th row. So I plus 1 has to be r plus 1. No, sorry, r minus. We were looking at terms in the r minus 1th row. Okay, so I plus 1 has to be r minus 1. So I has to be r minus 2. Okay, so we put this in here. We're looking at, you're right, I has, thank you, yes. So correct, thank you. The I has to be, as you said, r minus 1, because we're looking at the r minus 1th row. Thank you. So I is equal to r minus 1, so we just plug r minus 1 in here. Okay, so we get this coefficient is r minus 1 into r minus 1, so that's 1. And so on. Okay, so you see that in general, let's try to see if we can work out the formula for the, let's do f of m. Let's look at the mth row. Okay, so first we will get, of course, minus of f of m minus 1. Okay, then we will get plus some, let's say n is equal to 0 to infinity. Okay, now we want to get okay, it's going to be a bit complicated because we have to take this to some power. Okay, but it's just progressively multiplying this j plus. So let's see. So let me write out the first few terms and then maybe we can generalize. So we will get fm, L minus 1 fm plus L minus 2 into minus t into L minus 2 into a number. This number, as Omkar explained to us, was just what we got with j plus when we said I is equal to m. Right, because we are in the mth row. So we get m into r minus m. So minus t to m into r minus m. Okay, then the next term will be what? Yeah, so here in the next term we'll get t squared L minus 3, fm plus 1. Plus 1. So the next term we'll get plus t squared into L minus 3 fm plus 2. But now we would have had to raise twice. So the first time we raised from fm plus 2, I was m plus 1, because we raised to the m plus 1th row. So we get this factor twice. So we get m into r minus m times m plus 1 into r minus m plus 1 times L minus 3 of fm plus 2. And so this continues, right? We get the product of these terms with these guys constantly increasing. So we'd get product. Okay, so let's write that down. So that's minus f m minus 1 plus sum over L of, let's say, let's do the sth term. So minus t to the power s L minus 1 minus s f m plus s, and then the coefficient would be, well, we've raised up to m, But then we raised m plus 1, and how many such terms do we have? M plus s minus 1. And then we also get r minus m into r minus m plus 1 into r minus m plus s minus 1. Okay. So this is the expression, you know, and then s ends when you reach r. Right? When you reach the bottom row. So this is the expression for what you get when you act on this matrix. The expression for the rth element after you've acted with this object. It clearly depends only on the guys below it. Okay. So as we explained in the last class, it's obvious from the structure that if you use this structure to generate, the expression for f0 in terms of fr, it's obvious from the structure that f0 is, or fr in terms of f0. fr in terms of, no, was it f0 in terms? f0 in terms of fr, sorry. f0 in terms of fr. Yeah, it's obvious from the structure that what you're going to get will be level r higher, because you see fr minus 1 is level 1 higher than fr, fr minus 2 is level 2 higher than fr, and so on. It just keeps going until f0, that highest guy, which is the same as f0, which is equated with f0, is r levels higher than fr. So the way it works out. Is this clear? What remains to see is whether this f0 is level r higher than fr. Exactly. And therefore f0 has the right quantum numbers to be the null descendant of the primary state. If you think of fr as the primary, and you think of f0 as the descendant, then f0 has the right quantum numbers to be the null descendant of the primary. Clear? Okay. What remains though is to check whether it actually is a null descendant. Okay? In other words, what we need to check is that it's not just a descendant but also a primary. So what we want to do is to check that L1 and L2 annihilate the state, annihilate this descendant state. And we're going to show this by establishing a couple of things. Okay. Now, the first thing we're going to do is to demonstrate that the following equation. Okay. We're going to demonstrate that L1 on Fi is equal to L1 and F, he's got J, let's call it M, so you can read it. L1 and Fm is equal to M into R minus M by 2 into 2M plus 3 minus R times T minus 2 of Fm plus 1. Brackets, thank you. This guy is here. The thing that multiplies T is in a bracket, and this guy is not. Okay? So this is the thing we're going to establish for all values of n. Okay? First, in order to see this, Once we have this, what we want will follow up very easily. Okay. So before we actually try to establish it, notice that it's very interesting. You see, clearly Fm, okay, is R minus M levels above Fr. Okay, so Fm, if you think of Fr as the primary, Fm is a level R minus M descendant of the primary. So we act on it with L1. We act on it with L1, we'll get one lower level descendant of the primary. The point is that this one lower level descendant of the primary is precisely Fm plus 1. Or not precisely, proportionate. That the linear combinations work out in the right way. Okay? That is what is special about this operator. Yes. So this equation is going to be true for all values of m that are larger than r, and then when you choose m equals r, it will be true, but there's no fm plus 1, so just with 0. Okay, so then this will establish what we want. Right, it will establish what we want because it establishes that which way are we going? F0. No, that will not establish. This is true for all. When now we act on 0, it will establish what we want because of this factor of m. Yeah, so this is true for all, as written, it's true for all m greater than r. At m equals r, it's also true when you just set that thing to be 0. That's obvious, right? Right, because fm is the primary. So you act with L1 on the primary, you get 0. Okay, so if we, in our minds, whenever we see an fm plus 1, just replace it by 0, then this equation is always true. This is the claim. Okay? Excellent. So now let us proceed to take a look. Let's look first at the first guy. Okay? We had fr minus 1 was equal to fr with an L minus 1. So let's act on with L1 on fr minus 1. Okay? We act with L1 on fr minus 1. This gives us, take this L1 through. So we get 1 plus 1, so we get a factor of 2 and L0. So we get 2 L0 on fr. Okay? Now this L0 was h on this descendant was h r comma 1. And what is h r comma 1? L1, L minus 1 don't involve C numbers. Right? This was just the the factor in front of the C number was m into m square minus 1. Yeah, right. So this the SL2R part does not involve the C numbers. Yeah. Okay. Okay. Now we need to look at what this L0 and FR was. Now L0 and FR was simply the H of HR1, which we can find somewhere. HR comma 1 was here. Maybe it's a simpler form here. Just give one minute. HR comma 1. some very complicated formula. Let's say I have H r comma s was equal to r square minus 1 by 4 plus now r comma 1. So this is 0, r square minus 1 times t. Okay, it's not so complicated. Plus rs minus r minus 1 by 2. R minus 1 by 2. Okay. So let's check this. So we have, if we multiply this out, we get 2 into r square minus 1. So r minus 1 is common. So 2 into r minus 1 into by 4. So that's 2. And then this is r plus 1 into t plus 2. Okay. So this is our explicit computation. Now let's see what we get when we put it in here. Here we wanted to put m is equal to r minus 1. Right. So we wanted to put m equals r minus 1. So we get this factor of r minus 1 times 1 by 2. Now, this works? Okay, thank you. Okay. So this works out. There's with a minus. Thank you. Okay. So at lowest level, we've just explicitly checked this. Okay, it was a pain, but we explicitly checked it. Okay, now how do we proceed beyond lowest level? Well, we proceed basically by induction. Okay, claim that this is true. What we do is assume that this is the case for the, some level here, and check that that if that is the case, then it's also the case for the next highest level. Okay? Now this is easy to do because when we act with L, see we've got this explicit series there for what fm minus 1 is in terms of the lower guys. Okay? So what we have to do is to take that L through the other L's, and then, thank you. And then when the L minus 1 goes and hits the other guy, we already know what it is because by assumption we know what it is for all the lower levels. Okay? So now this algebra is daunting, and I'll get it wrong and I'll take 20 minutes, but you know what to do, right? And I'm just going to let it be. Okay? So you take that equation that we've written down, and we act with assume that this equation is true up to some level, starting from below. And then check that it's then consistently true for one high level. Okay? When you work hard enough, you can do that. Okay, just algebra. And this then in particular establishes that F0 is annihilated by L1 because of that explicit factor of M. Is this clear? Okay. Now, in order to check that it's a primary, we need to check not just that L0 annihilates it, but also that L1 annihilates it, but also that L2 annihilates it. Same strategy. Same strategy. I'll just write down the inductive relation that one can check. L2 on Fm is equal to T by 4 times M into R minus M into m plus 1 into r minus m minus 1 into 4m plus 6 minus r t plus 7. So quite a mouthful on f m plus 2. Okay. Once again, this is true. You should replace f anything greater than fr by 0 in this relationship to make it true. Okay. So once again, the first step would be to check it for the second lowest level. So L2 and f r minus 2 is something into fr. This gives you a prediction of what that something is, and you check that number. Of course, it had to be proportional to fr because it lowered it back by 2. The only question is the number right? Okay, that sets up the first step of the inductive procedure. And then you assume it's true, and once again by induction, show that it's self-consistent. Okay, so all these things, when you know the answer, are very easy to prove. Of course, getting the answer is another matter, Okay, but of course, people had all kinds of intuition, and people worked really hard on this. Okay, fine. So following this procedure, you establish, you verify, okay, you verify that this is indeed the null state. Okay, so this completes our proof. We've actually found the null state for the level f r comma 1 for f r comma 1. Okay, excellent. Excellent.
Was there a reason to, or is there some way to see why this form D works?
Yeah, I'm sure if you have enough, where did you get it from, right? Yeah. One way of asking that question is how, say, I don't know. Okay. I'm sure the people who have worked hard on this, no. What is the relationship to SU2, for instance? And what other groups show up in other levels and so on? I don't have a good answer. I'm sure the answer is the right person knows, but I don't know. Laplacian. Please say a little more. Yeah, well, there's one thing to say. There's one thing to say, which is, yes, exactly. You could try to take a c goes to infinity limit of this problem. In the c goes to infinity limit, okay, in a sort of classical limit, these Virasoro operators are represented by differential operators. Okay, and the problem of finding null states becomes a problem in classical differential geometry. Okay, I do believe that this is the origin of this. I do believe that the people who thought this up were very much inspired by that. You search for that problem, you look at that problem in the classical theory, and then try to make a quantum deformation of it. I do believe that this was the historical path. Okay, but I won't swear on this, and yeah, but I think that what Karthik is saying is correct. That there was a differential classical picture, which then was quantized. Sort of, you took it as inspiration and quantized it. Yeah. Yeah.
Would one think of this as, a homological series with, differential operators D, so that D dagger plus D dagger D is your Laplacian. That would give you.
You're thinking of this as like cohomology, you're saying?
Yes.
Okay, interesting. Now, what would your cohomology operator be?
Yeah, that's what I.
Yeah. Yeah. You know, this kind of thing we do when we look at BRST quantization.
Right.
And it's true that null states are intimately tied up with, so maybe there is a way of thinking of it that way. I suspect you're right, but I don't know. Okay, it's true that null states are at the heart of this BRST business. Yeah, so may well be. Yeah. Okay.
Coset construction doesn't give any answers.
Coset construction gives the answers in some different form. It gives you the answer very, very easily. Maybe, but I'm not obviously.
Are the null states analogous to the trivial class if you try to construct a homology?
The null states would be the states that are, for instance, usually are the states that are Q exact. Yeah, so just 0, cohomologically equivalent to 0. Yeah, okay, all good suggestions. All of them may have something, I just don't know. But okay. Okay, excellent. So we're oh wait, I had to make 2 or 3 comments on this. Okay, now the first comment is this. Look, we wrote down f m minus 1 as a series in terms of the lower guys. Okay, by iterating that series, okay, it's sort of clear that if you work a little hard, you'll be able to write down an explicit expression, not just for fm minus 1 in terms of fm, but fm minus 1 in terms of fr. Right, because all of those other guys you keep using that series again and again. Okay, so by doing that you can generate an explicit expression for each of these fm's in terms of fr, and in particular for f0 in terms of fr. So not just this procedure, but very explicit form for the for this operator, for this null state. And I'll just write that down for you just so that it's not very pretty, but okay. Pi greater than equal to 1, P1 plus Pk is equal to R. At this, I'm just writing down the expression for F0, the final null state. Okay. R minus 1 factorial, the whole thing square, minus t to the power r minus k, and then product, even before a question that you might have asked is, why in this expression did we have to use the t that was the t that defined the central charge, or the t that was p prime by p? Okay, and we see that from here, right? We wouldn't have got this matching, this relationship between Lm and Lm minus 1, and that involved this t. And where did that t come from? It came from the charge of the primary. Is this clear? This is the reason we had to use that t, the t that involved the central charge in this relationship. We couldn't use any number, it had to be the correct one. And the place where we use it is to get the charge of hr comma 1, the dimension of hr comma 1. That involved t. That's why this t was involved then. Just to say that. Okay. And okay, so okay, this is really very unilluminating, but anyway, I is equal to 1 to k. P1 plus P2 Pi, R minus P1 minus P2 Pi, L minus P1, L minus P2 up to L minus Pk of the primary. The explicit expression doesn't matter. I just wanted to emphasize that there exists an explicit expression, and you can look it up from the big yellow book if you ever wanted, and pray that there were no typos. Okay. Okay, excellent. So that's all I wanted to say about the explicit form of the null state for this particular r comma 1. If anyone's particularly interested, I could give you a discussion on more general null states. But for now, let's move on. Okay, as you see, this is a very technical topic. Okay, it's a very technical topic that has been worked on very thoroughly by many very smart people. A lot is known about it, and each result is technical. Okay, so to really understand this field, we need to get into these technicalities. I'm sorry about it. I know it's not so much fun to do these kind of things, but unless we do it, we don't feel we understand it. Okay, so with that apology, I'm proceeding. Okay, excellent. Now, the next topic I wanted to move on to was to move on to a more detailed study of the differential equations that come from null states. Okay, this is really important. For instance, in the case of the Ising model, it allows you to completely solve the theorem. And in the case of Westermino-Witten theories, the differential equation of this sort, the most famous of these, the so-called Krzyznik-Zamolodchikov equation, both allows you to solve the theory and also gives you great insight into the structure of the theory. Right? So these differential equations are very, very important to this study. So let's take 40 minutes to look at them. Okay. So first, what is the nature of the differential equations? Why we have differential equations we've already studied, right? You act with some differential operator. You act with some descendant on a state you get 0. But you remember we could take that descendant, write it as a contour integral around our operator, and then take that contour integral and move it around all the other operators. You remember that? Okay, so this relationship turned, and that motion into around all other operators turned into just differential operators on those other operators. So the fact that there was a null state turned into a clear differential equation on correlators. Okay, and I'm just going to, in 1 minute, abstractly write down this form. It goes this way. Suppose you wanted to act with L R minus K, RK, L R K minus 1, L R1. So you wanted to take, and all of these are minuses, some particular descendant of a primary on phi 0. Okay, you wanted to take this descendant and look at its correlation functions with phi 1 to phi whatever else, m. We need this general form of having many operators because you remember, because as you've seen, our null states in general are sums of products of these many descendant operators. Okay, so actually let's reverse the order. Let's do it L minus RK, because then it'll, when turning it around, it'll act with RK on this guy, and you know. Okay, so L R minus R minus 1. Now this, we argued, was the same as the following. Okay, it was the same as L minus R minus R1, L minus R2, L minus Rn, which now become differential operators acting on phi 0, phi 1, phi m, where L minus R is equal to sum over I is equal to 1 to m, R minus 1 hi divided by zi minus z. So this guy this is L minus R of z, and these are all acting at the location of this guy. So let's say this guy was z. Okay, so this guy was at z, and all the rest are wherever they are, z1, 2. So to the power r minus 1 by zi minus z, the whole thing to the power r minus 1 del zi. So each of these guys, remember, acted on each one of the other operators, because you took this contour around and circled all of them. That's why we have this sum. You took this guy and moved it. You got this sum. Then you took this guy and moved it. You got the other sum. And that's what we've written here. Is this clear? So these differential operators acting on that correlator give you the action of that descendant, of the correlator of the descendant of phi 0. Now, we're going to use this in the following way. We have that, there is some alpha y ly sum over y with mod y equals n naught. I'll tell you what y is in a minute. On our primary is equal to 0. Now what is this? Y is a tuple of numbers, is equal to R1 to Rk. Okay, and it's this tuple such that R1 plus R2 up to Rk is equal to mod y. So this is the total descendant level. Okay, and alpha y dot ly tells you that you have, if you have R1 Rk, you will have Lk, Lk minus 1, K minus 2, and so on, with some coefficient. Is this clear? So when I give you this y, Ly is the product of L's with these numbers. L minus Rk, L minus Rk plus Rk minus 1, and so on. And then the coefficients of that is some alpha y. We're trying to build a descendant at some given level. That's why we take all possible products of these L's such that the total level number is y. So this is some descendant at level mod y.
R1, R2, Rk are the partition of the number 1.
Exactly. So what we do, as Jan said, is you take y, partition it into integers in every possible way. Every possible integer partition gives you some L's acting on the primary that comes with a coefficient, and you multiply that out. You sum over all possible ways. Okay, so that we know in the case of r comma 1, we know exactly what these alpha y's are. That's what we wrote down up there. Right? But in general, this is the structure of a null state. Something like this. So we want to take, we know what any one of these Ly's looks like. That gives us this thing. We want to weight each of these with some given alpha y and sum over all y's and get 0. That is our differential equation. This is the structure of the differential equation acting on correlators. This is clear? Okay? Now, Now what we're going to do, is to look at 2 or 3 things we can do with these differential equations. The first thing we can do is the following. Okay? The first thing we can do is the following. Suppose we've got a minimal model. Okay? Suppose we've got a minimal, these differential equations will become more and more complicated when they act on higher and higher correlation functions. The first place where it becomes really interesting, and we will consider that in this lecture, is the 4-point function. But we're going to try to milk whatever we can from acting on lower point functions first. Okay? So the first thing we're going to do is to see what we can say about the consistency between this differential equation and what we know about the structure of not even 3, but 2-point functions.
But didn't we do this when we found the fusion rules of these 3-point functions?
Yes. So there we use that to find some constraints on fusion rules of 3-point functions. Yeah. What we're going to now do is to find a constraint on the nature of the null state itself. Okay? So there we acted with these differential operators on 3-point functions. Yeah. We're now going to do something even simpler. We're going to act on 2-point functions and see what happens. Okay? So what is the idea? Okay. So let's say that we have our original state, okay, our original primary, which has some weight which we'll call h naught. We know that phi h naught of z times phi h1, where this is some other primary, of 0, okay, this is equal to delta h naught h1 times 1 over z to the power 2 h naught. So primary can only have 2-point function with something else of the same weight. Anything that has different weight, we'll have to get 0. This we know. Okay, we normalize our primary so that coefficient is 1. Okay, sounds good. Now we do the following. Okay, let's apply this where h1 is equal to just h naught itself. So we get phi h naught of z, phi h naught of 0 is equal to 1 over z to the power 2 h naught. Okay, we're going to take this expression, which we know to be true, and act on the first phi h naught with the null state condition. Right? So this differential operator has to annihilate every correlator. In particular, it has to annihilate the correlator associated with 2-point functions. Okay? And if everything is matching up, this should work out somehow automatically. But how is it working out automatically? That's the question. Question clear?
So phi h naught is a null state.
Phi h naught is a primary, which has null states. Okay? Because we're looking at minimal models, all primaries have null states. So we find the null state operator, the null state of this primary. For instance, it could be r comma 1, we've just found that null state. Then we act with the corresponding differential operator just on this function. And then we have to get 0. Question is, how is it working out? Okay? So of course it must be automatic, but there is, suppose we didn't know these alpha y's. In the case of r comma 1, we knew these alpha y's. Suppose we didn't know these alpha y's, does this condition give us some sort of constraint on the alpha y's? Question. Okay, so now what we're doing is using this idea just to constrain the form of the null state. Okay, fine. So we can proceed with this. Okay, so Okay, so claim, suppose I act with this, first now, since we're looking at 2-point functions, that L operator is simple because the sum in that L operator goes away. Right? We're acting with the guy on the first phi z, then we transfer it to the second phi z. So all it is just one differential operator acting on that h. Okay? Now we just have to look at what that differential operator is acting on the h. Okay, so let's just work it out. Let's work out what L minus R is acting on this this function. Right? So that is R minus 1 h, which is simply this h0, by z1 minus z. Okay, z1, so let's say that this other guy was 0, so this up to sine is z, it's minus z. Right? So 0 minus z to the power r, so minus z to the power r, minus 1 by z1 minus z, so minus z to the power r minus 1, del by del z. Okay, let's write this as z minus z1. Okay, to the power 2h. Then this is z1 minus z to the power, this is z1 minus z to the power minus 1, del by del z1 on 1 over z minus z1 to the power 2h. Clear? Okay, now let's work this out. This guy is some number times z minus z1 to the power 2h plus r. Same with this guy. Because when we differentiate this, we get 2h plus 1 and then this multiplies by r. Okay? So what we get is 1 over z1 minus z to the power 2h plus r times some effective number. Okay? And this is going to be true every time we act. So what we will get in the end is if we act with a descendant at level mod y, this z1 minus z will have, the power of z1 minus z will have become 1 over z1 minus z to the power 2h h naught plus mod y, and we will get some effective number. Okay? And in the end we work out this number. That number has to be 0. So this is the constraint we get from this point of view. Okay? So we work this out and we get some number is equal to 0. Okay? Okay, so that, from this point of view we get one constraint. Okay? We get one constraint on the set of these alpha y's. Okay? That appear. Now one can actually show both abstractly as well as explicitly that this constraint is obeyed from the form of the original null state. Okay? And the way it goes is as follows. Suppose you've got your null state. Suppose I've got my null state, which is primary times some level n, let's say a level n naught descendant, level mod y descendant. Now if I act with L1 to the power mod y on this must vanish because L1 annihilates the descendant, so L1 to the power mod y must also annihilate it. But L1 to the power mod y on this descendant is once again proportional to the primary. Because, you know, the descendant was mod y levels higher than the primary, and then L1 to the power mod y lowers it again back down to the primary. Clear? So once again, algebraically, if you act with L1 to the power mod y on this descendant, you will get some number times primary. So the condition that L1 annihilates the state is very powerful. It almost completely determines the state, that and L2. But the condition that L1 to the power mod y annihilates the state is much less powerful. It doesn't give you a constraint, a full constraint of the state, just gives you a constraint of one number, so one set of linear combinations of these alphas. And the relationship that you get by acting on this 2-point function, the one we just discussed, turns out to be exactly identical to what you get from here. Okay? Therefore, the picture is consistent. It's, you might have worried that you would have got an inconsistency by acting with this differential operator on this 2-point function. Given we already knew the form of the 2-point function, and we already knew the form of the null state. But of course, this inconsistency does not appear simply because the relationship you get can be derived from the relations you used to derive the null state. So it's just one of them. Okay, the book works this correspondence out in detail. Again, I don't find it particularly illuminating, so I'm letting it go from here. Okay, just to give you the logical flow here. Was that good? Questions or comments about this? Then we move on to 4-point functions, where the real meat is.
Somehow, these 2-point functions of two operators are on the plane.
Yes.
It's basically related to inner products of
Exactly. Exactly. So as you are indicating, the reason that this as you are indicating, somehow the reason that this works is as follows. We've got like a primary here. We act with the null state. Okay? And so we've got a primary, we act with the null state. And then what did we do? Okay, good. Can you convert what you said into an argument that this is precise? Can you predict from here that it was the L1 to the power n mod y? You're right that basically we're acting with this thing inside matrix elements.
Yeah.
But it would be nice to see from there that we should expect that the one number we got out of this was
Is it not true that 2-point function of two operators will be zero if their correlation function is 1?
if their correlation? Sure.
So, I mean, if we just do a conformal transformation of this
Yes.
equation to the cylinder,
Yes.
we should be getting the same constraints that we are.
No, of course, we are getting the same constraints. I mean, the whole thing is fitting together, right? But there is a very particular statement here, which is that when you act with this differential operator on this 2-point function, we get exactly the same condition as acting with L1 to the power mod y on the null state.
Yeah, so we could do one thing. We could insert an operator at 0,
Mhm.
the other at infinity.
Okay.
That basically corresponds to computing the NF effect on the cylinder.
Good.
Right. So if you insert this operator at infinity,
Yes.
that will kill the power that is in the denominator. Z minus
That's fine, yes.
to the power some.
Okay.
And the only thing that you have got is the coefficient.
Okay.
That should be zero.
Well, at the moment you've only talked about the 2-point function. Are you acting with the null state?
Yeah, the state is done. The other, I'm computing the 2-point
I-
function of a null state with some other state here.
Right. Are you computing the 2-point function of the null state with the primary, for instance?
Primary.
Okay, excellent. So that sounds exactly like what we're doing in the differential equation part.
Yeah.
We're computing 2-point function of null state with primary.
Yeah.
Okay? And of course it had to be 0 because the null state was 0.
Yes, but I'm saying the coefficient is basically something that you will also get by when you compute the inner product of a null state with some other primary state.
Sorry, what I'm not understanding from this argument is how we would have seen that we recovered this relation from L1 to the power mod y. You know, this particular test is working for any state provided for any one of these putative null states, provided only that the coefficients alpha y obey one condition. Right? It did not actually have to be null. All that was required was that L1 to the power mod y annihilated it. You know, so really satisfactory explanation along these lines would have to show that feature. Okay? There probably is one, but I'm not saying it. Okay. Excellent. Excellent. Yes?
We can also fix the normalization for the space.
Yes.
And then we can also fix the form by SLTC invariance. Right?
Form of 3-point function? Well, the 3-point function normalization at the moment is unknown. It's meaningful but unknown. Right? We have to determine it somehow.
How do we usually do that?
We do it by solving for 4-point functions. So the 4-point functions then tell you the answer. Okay, we're going to there. Okay, fine. Now as the next exercise, what we're going to do is to try to use the structure of this differential equation to work out the 4-point functions in the Ising model. Okay. So the 4-point function in the Ising model, well, what we're going to do is to work out the 4-point function for any 4-point function that involves the first non-trivial operator phi 2, 1. So consider you have phi 2, 1 of z, then phi 1 z1. We don't even say what these other guys are. Phi 2 z2 and phi 3 z3. These are primaries, and there is very few possibilities for what they could be. But for whatever they are, we're working. Okay? Now, in this case, it's all very easy because this null state condition was a very easy one. Either by looking at the specializing what we did here to phi 2, 1, or using what we did right at the beginning of the class. Right? We worked out explicitly the form of this null state. We just write down what the null state is. Where is that? It was L minus 1 squared and L minus 2, but with some linear combinations which I'm searching for. 8.46. Sorry. We'd worked it out some time ago. Let me find it. Sorry. Yeah. Okay, excellent. We had the differential equation was L minus 2 minus 3 divided by 2 into 2h plus 1 del 2 by del squared. Okay, and now we can put in what this h is. We can put in what the h is. By putting in, what was the dimension of phi 2, 1? Was that half or? Sorry, let me look that up. This is phi 2 comma 1 yeah, is half. Okay, so we put in this value of phi 2 comma 1 so that we just get L minus 2 minus 3 by 4 d 2 by dz square. Okay, and this L minus 2 was listed up there, right? So what we have to do is to act with this operator on the sum of these three things. Okay, so we're going to get a very particular differential equation. Now we're going to simplify our lives by using conformal invariance. It looks at first like the 4-point function depends on four guys, z, z1, z2, z3. But we have already seen that all correlation functions are SL2 are invariant, right? That they're translation invariant, they're scale invariant, and they're also annihilated by special conformal transformations. Okay? And a very simple consequence of this fact is the following. Suppose I take a 4-point function. Okay? Suppose I take a 4-point function of 4 operators whose dimensions are h1, h2, h3, and h4. Okay? Then this 4-point function must take the following form. It must take the form, okay, I'm writing down the form that the book gives. Product 0 less than equal to, let's say h0, h1, h2, h3. Okay. I less than j less than equal to 3. Zi minus zj to the power mu ij g of z, where mu ij is equal to 1 by 3 sum over h minus hi minus hj, and z is any of is for instance the cross ratio z0 minus z1, z2 minus z3 divided by z0 minus z3, z2 minus z1. Okay, first is this claim clear, then we will try to understand it better. Is the statement of the claim clear? Okay, so the statement of the claim is that, you see, there is a part of the correlator that we choose arbitrarily that exhibits the right conformal transformations that we expect from a 4-point function. This is that part. This product. We've chosen something by trial and error that has the right conformal transformation properties that we expect from a 4-point function. Then we multiply by anything else that under SL2R transformations remains invariant. So then that times the candidate that we multiplied by will have the right transformation properties under SL2R for a 4-point function. Now, of course, the prefactor was not there was no canonical choice for it, because I can multiply that prefactor by any function of z. That will amount to a redefinition of this g of z. So there's no right choice or wrong choice for this prefactor. The prefactors are only well defined up to multiplication by functions of z. It's sort of like, if you've got a differential equation, you've got a homogeneous part and a forcing part. Then there's a particular solution plus an arbitrary homogeneous part. Now there's no particular good choice there's no canonical choice for the particular solution, because to the particular solution you always add any linear combinations of the homogeneous solutions. It's very much like that. Good. The second one is involving z bars. Okay, so we're talking only about the holomorphic part. So we will have the holomorphic part and the anti-holomorphic part. Okay, in higher dimensional conformal field theories, the split between holomorphic and anti-holomorphic is not so clear. There's some sense in which vaguely it can be made to appear to happen, but there's no real clear split. Okay, so there we just have to look at the two together. Okay, but here, because everything splits between holomorphic and anti-holomorphic, there's effectively just one. So that's a great simplification of 2 dimensions. Okay, now let's look at this product a little more carefully, just to look at it. Okay, let's look, for instance, at the total weight that appears in mu. Okay, so this mu here involves I less than j. So there will be a mu 01, mu 02, mu 03, mu 12, mu 13, and mu 23. There will be 6 such terms. Okay? Each of these 6 terms comes with this sum over h. So from this sum over h, we get 2 times sum over h. Clear? Because 6 into 1 by 3. Okay? From this guy, what do we get? Okay? So let's just total it up. So we will get h1 plus, for all these cases, we'll get strange, hi. Each hi and each hj appear exactly 3 times. Yeah, that's probably right. So so we get h0 plus h1, h0 plus h2, exactly. h0 plus h3. Then we get h1 plus h2 and h1 plus h3, and we get h2 plus h3. So as Omkar said, h0 appeared 3 times, h1 appeared 3 times, h2 appeared 3 times, so on. Okay, and therefore we get minus 3 times sum over h. Okay, so the whole thing scales like z to the power sum over h downstairs, which is what you expect from the weight of a correlation function. Okay, now if you play around with this form, you will find, for instance, in the case that you have 2 operators of equal, let's say h0 and h1 had same dimension, and h2 and h3 had same dimension. Okay, then this prefactor can be written as 1 over z0 minus 1 over z0 minus z1 to the power 2h0 times 1 over z1 minus z2 to the power 2h whatever h of that, times maybe some function of this cross ratio. This had to be, because you know, when you have a 4-point function, when the operators are equal weight, then one way of satisfying the word identity is just write it as a product of 2-point functions. Can't satisfy the word identities like that unless they're equal weight, because the 2-point functions only satisfy word identities when they're equal weight. Okay, so this is why it's more complicated in general. But when the operators are equal in pairs at least, the prefactor can be written in a very simple. Okay, this satisfies all the word identities. I'll leave for you as an exercise to check. Okay, we worked out what the word identities were, if you remember in an earlier class, just the differential equations. The only one that's non-trivial is the special conformal transformations, the L minus 1. Okay, that's the only one that's non-trivial, and that these satisfy the word identities. I'll leave you to check. Okay. So now this 4-point function has one unknown structure, namely this g of z. Now what we want to do is to take this differential operator, okay, and act on this differential operator has to act on the sum of all 3 other guys. Right, we've got one special operator, 3 other guys. We take this differential operator, act on the sum of these 3 other guys, and we should get 0. And that is our, that's what we expect. Now, there's only a little bit of irritating algebra here. The irritating algebra takes the following nature. The differential operators act on Z1, Z2 and Z3. Whereas we have represented our object as a function of this Z. But of course Z was a function of Z1, Z2, Z3. So when you act on G, let's say with the differential operator and del, let's say del by del Z1, that is, you just use the chain rule, right? That's same as del by del Z times del Z by del Z1. Okay? Also you have to act on the prefactor. Okay, so this is the kind of sort of irritating algebra you have to go through. It's all outlined in great detail in this yellow book. What is to be done is clear, right? Okay, I will just give you the final answer.
So one thing is that when this discrepancy people, for the 4 point they do that, you can fix 1 point to infinity,
Yeah.
1 point to origin,
Yeah.
and 1 point at 1, 0.
Yeah.
And this third guy will be the cross ratio, then will become just the value of the third guy.
The second is what
Yeah.
people only say. Yeah.
So then the equation, won't the equation simplify now?
It will, but you have to be careful. You shouldn't set these guys to 0, 1 and infinity before taking the derivatives. After taking derivatives, you can set them to whatever points you want. But what does del by del Z1 mean if Z1 is 1? You understand? So we first keep these points arbitrary, then we take the derivatives, then after you do that, you can choose whatever points you want.
So we have to go through this painful algebra.
We have to go through this painful algebra. This is not, not negotiable. Okay? Okay. In the end, though, you get a constraint only on the function g of z. All this stuff is dressing jazz. The differential equation is the differential equation on g of z. Okay? Now, I'll just write out the fine. I'm not going through the algebra. It's given in great detail in this book, and there's nothing that's not obvious. Okay? It turns out to be, in the case of the Ising model, better to work with the following hz is equal to z. We said that we could absorb into this prefactor any function of cross ratios. Right? Turns out you get a better differential equation by choosing a different prefactor. That is, we get a better differential equation for z to the power mu 0, 1, 1 minus z to the power mu 0, 2 times g of z. So define this function, which is the unknown function with a different prefactor chosen, and that function turns out to be the differential equation del z squared by t plus 2z minus 1 by z into z minus 1 minus h1 by z square minus h2 divided by z minus 1, the whole thing square, plus h0 plus h1 plus h2 minus h3. Plus h1 plus h2 minus. You might have wondered why is there lack of symmetry between 1, 2, and 3? It's because we've chosen the prefactor in a way that is not symmetric. That has 0, 1 and 0, 2, but not 0, 3. Okay? So the original choice of prefactor was very symmetrical. This choice is not, but at least a simpler differential equation. Okay? This is some differential equation. Now this differential equation, for those of you who know such things, is a hypergeometric equation. Okay, so you put it in Mathematica, it will say hypergeometric 1 something. Okay, so to the extent that you consider hypergeometric solutions known, this is the answer to this equation is known. Okay? How many solutions you have? You have 2 solutions, because second order differential equation. Okay? So the most general correlation function, okay, involving this operator. So say we had this phi 2 1. So we've got some, let's call the solutions H1 and H2. And let's say that this, we're looking at the modular invariant, the diagonal invariant, so that we have H1, H2 on the left. Sorry, that we have this operator 2, 1 on the left and also 2, 1 on the right. And the operators in the same representation left and right. Okay? So then the most general correlation function involving these 4 operators has to be of the form alpha 1 1 H1 of Z H1 of Z bar plus alpha 1 2 H1 of Z H2 of Z bar plus alpha 2 1 H1 of Z H2 of Z bar, sorry, H1 of 2 of Z H1 of Z bar plus alpha 2 2 H2 of Z H2 of Z bar. But these functions are just totally known. So you've reduced now the problem to finding a correlation function in a quantum field theory to a problem of determining 4 numbers. Alpha 1 1, alpha 1 2, alpha 2 1, alpha 2 2. Totally amazing, right? It's totally amazing. Now, actually, this particular conformal field theory, which is free fermion theory, we had other ways of solving. So it's not as amazing. But when you go to the slightly higher minimal models, very similar things happen. The similarities, it's very similar, except that instead of getting 2 solutions, you get RS solutions. Right? Because your differential operator, the degree of your differential operator, is basically the level of the state. Okay? And the state will appear at level RS. Okay? So you'll have RS solutions. These RS different solutions in this context are called conformal blocks. Okay? And what we are saying is that the most general, there's a finite number of conformal blocks. It's a pain when it goes to 20, but okay. It's a finite number of conformal blocks. And the most general solution for the correlation functions of the theory are given by an RS times RS matrix of numbers, which you have to then determine. How we'll determine that? We're coming to. Modular invariance, single valuedness, all of these get related and play a key role. But we've already, also there are more constraints, because in these minimal models, you can use the results for all null states. We've only used that this operator had a null state, but all 4 operators have null states. Okay? So we've already brought it down to some finite problem, but it's clear there are many other constraints. And as we will explain as we go along, maybe in a lecture or 2, maybe 3, 4, maybe we'll do the Coulomb gas formalism first. Then when we look at the constraints for modular invariance and single valuedness, we will be able to completely determine these numbers. Okay? So once we have these 4-point functions in hand, we can find all 3-point functions, because we just factor this 4-point function on poles. We take this 4-point function and check its consistency with the OP. It will be consistent with the OP, provided we have some particularCijks, and that determines theCijks. Okay? The OP is a very simple OP because it involves only a finite number of fields, because the total number of fields in our theory is finite. Okay? So this turns out to be the easiest way to determine the 3-point functions. To find the 4-point functions and read off the 3-point functions from. Okay? Excellent. Excellent. Any questions or comments about this? Okay. Fine. I think there's, in this book now, I mean, I have the feeling this course is getting too technical. But what to do? Yeah, okay. This book now goes on to describe more about the fusion algebras in chapter 8. My suggestion is just so in the interest of keeping interest of the audience, we'll skip that part. And, and move on to the description of the Coulomb. This is more fun. This Coulomb gas formalism. And so next lecture we will describe what is called the Coulomb gas formalism, which is an explicit way, in a way the physics way, of computing correlation functions of in minimal modulus. And when we move on to the study of modular invariance, that is fun. There's lovely things like the Berlinde formula and so on that we will see. Okay, so I think there are nice things about the fusion algebra. There's this fusion ring, but I will postpone it to when we need it. Okay. Okay.